All right. So this is what we're going to do with the support vector machine. We've already defined the support vector machine optimization problem at the beginning of the lecture. Now what we'll do is we're going to massage it a little bit. Remember, the support vector machine was not differentiable. We're going to massage it a little bit into a quadratic program, which is a nice form. You could feed it into quadratic program solvers. And then we're going to start down the path of deriving the dual formulation. I'm going to skip some steps because they're a little bit tedious, and you can work through them in the notes. Not too difficult, but just a little tedious to do in this format. And when we look at the final dual, we're going to be able to extract some interesting insights right away about the support vector machine from just the dual. And then we're going to apply the complementary slackness conditions. And then we're going to get some more interesting insights from the support vector machine result. And at the very end, we'll talk about the intercept term if we want to have an unregularized intercept term in the support vector machine. It turns out to be a little bit of a pain, but we can work through that quickly. So here's the objective function we wrote down at the beginning. I don't remember if I had it at the beginning, but I've now added an intercept term b. This is one classic formulation of support vector machine. It's not just w transpose x as our prediction function, as our score function, but we have this offset intercept term b, or bias term. So the score function is now an affine function. OK, so this would be the optimization problem we're dealing with. And so it's unconstrained, which is nice. It's not differentiable because of this maximum, which is not nice. And the question is, one question is, can we reformulate it as a differentiable problem? So we'll transform it in a few steps. And I believe this was in the notes, the pre-lecture notes, if you wanted to look into them. But it's very simple, really. So what's happened here is we have taken this expression in the maximum. Note that each summand is indexed by an I. So we introduce a new variable, psi I. And if psi I were equal to maximum, it would be exactly the same as this expression. But we've written inequality. Psi is greater than or equal to the maximum. And so my question is, are these equivalent? Yes. Yes? So they should be equivalent. Why? We're trying to minimize this whole thing. If psi I were strictly greater than the maximum, we could reduce the objective function by reducing it to be equal to the maximum because we're summing the psi i's. So the solution to this problem would never have psi I strictly greater than the maximum. The solution would always have psi I equal to the maximum. And if they're equal, you could just sub it in, and then you'd have the exact same problem we started with. So equivalent problem so far. All right, now we can look at the psi greater than or equal to the maximum of, it's the maximum of 0 and this more complicated expression. And we could break that up into two inequalities. So if psi is bigger than the max of two things, that's equivalent to saying it's bigger than the first one and bigger than the second one. Let's do that. So I've broken this out. Psi I bigger than the first, psi I bigger than 0. Let's rearrange that a little bit to make it like our standard form. So our standard form is the constraint functions are less than or equal to 0. So let's rearrange a bit. Now both are less than or equal to 0. All right, let's pause and see if what we have is a convex optimization problem first. So we need, when it's in the standard form, we need every function to be convex. So in the objective, first of all, what are the variables that we're optimizing over? First of all, W and yes, psi, right, psi. So our optimization variables are the vector W and the vector of psi i's, first of all. OK. What are the W, the y i's and the x i's? How do those fit in? Are those variables we're optimizing over?
Input and output.
Yeah, those are training data, and they're like built into these constraint functions. They're part of, so the constraint function for this constraint has xi and yi built into them, like as numbers. Oh, there's one other optimization variable, b, Didn't notice that. B.
I actually wanted to talk about that. Can you give a bit more intuition as to why we want to add the bias term? I couldn't quite figure that out even from the homework. Like, what's the benefit of having the bias term?
The benefit of a bias term? Well, so are you asked? So in the homework, we talked about it's some situations equivalent or some situations almost equivalent to put a feature that's always 1. Are you asking why we even do that, or are you asking?
Yeah, essentially.
Okay.
Why do we do that?
Well, that's just about the hypothesis space that is possible. So if your input space is just reals, for instance, the trivial is just reals, and suppose it's a regression problem, then if you only allow linear functions of x, your hypotheses always look like this.
Yeah, I guess my question was more at the end when we try to solve it, we essentially rewrite theta and x. So we rewrite our input space to include an extra dimension so that we go back to the linear space.
That's right. So you're asking why do we do that?
So if we are going back to being linear, what's the benefit of having this extra dimension?
So I think what you're asking is, so you're not asking why do we want the extra dimension. You're asking why do we want to explicitly have b if we have this whole problem on the fact that you can build b into your input with a feature that's always 1. Okay. So in the homework, you'll realize that when you have regularization, sometimes you don't want to regularize b. So if you just put it as, if you put just 1 as an extra feature, the hypothesis space is the same. You can make the same functions as if you had a separate intercept term, but when you fit, you're going to be regularizing that intercept coefficient. And maybe you don't want to regularize that for various reasons. And so also in the homework, we found that if you make your kind of, instead of adding a 1, you add a very large number, that's almost equivalent to not regularizing it, because you only have to put a very little, because it would correspond to a very little parameter to make your intercept that you want. So it would hardly be regularized at all. But it's still not exactly unregularized. So in this case, b does not show up in the regularization piece at all. Is that clear? So if you wanted to make this exactly equivalent to just add 1 into the feature vector, we would have to add a norm of b squared here too in the regularization piece. And then you could absorb it into the features. So a lot of people leave this out. I think it's not elegant to have that extra b piece. You don't really need it because you can make 1 or a large number as a feature. But a lot of people prefer this way, and so this is a little bit harder, and I wanted to give you the full generality so you have all the flexibility you need. All right, so this is our standard form. Oh, we're discussing whether this is convex or not. So we found our primal variables, b, w, psi. OK. Is the objective convex? Yeah. So this piece, this is quadratic. This is linear. So this is a quadratic function. It's not every quadratic is convex, but this is in particular, if you remember, this was one of the examples from our convex function. So we have a norm square. This is convex, and it turns out to be it's quadratic as well. So how about these guys? Are these convex? Now, they have to be convex functions of what? Of the optimization variables, right? So psi as an optimization variable, is negative psi convex? Yeah, it's linear, so yes, it's convex. How about this? Is this thing convex? What optimization variables show up there? W, NB, and psi I. But remember, xi and yi and 1, these are all just numbers. So if you multiply this all out, this is nothing but a linear function of wb and psi. So this is linear. So both of our constraint functions are linear, so trivially convex. Great. So we have this convex quadratic objective function, f0, and linear constraint, or affine, not linear, I apologize. The difference between affine and linear is the bias, the constant terms. So things that don't multiply at one of our optimization variables. So this is not only is it convex, it's quadratic objective, convex quadratic objective with linear constraint functions, affine constraint functions. That's a quadratic program. So you could solve it with any off-the-shelf QP solver. It's differentiable objective now. We have constraints, though, so that's the trade-off. It's a little bit more annoying to have constrained optimization. OK. But this is support vector machine as a quadratic program, and it turns out this is a nice formulation to take the dual of. So that's kind of our next step. All right. So we'll start down the path, and then we'll defer to the notes at some point. But what would the first step to find the dual be? So we have to first introduce some new variables, right? Lagrange multipliers. You get one Lagrange multiplier for every constraint. So how many constraints do we have from this line? N. We have n constraints, one for each of these psi's. And then for this one, another n, right? So we make, let's let lambda I be the Lagrange multipliers for the psi I constraint and alpha I for the other one. And now we can write down the Lagrangian. It's just a recipe. The Lagrangian, remember, is the objective function plus lambda I, or plus Lagrange multiplier times each of the constraint functions, and to form a little linear combination. So did we do that here? So we have this first piece up till here. This is the objective function. Now we have the linear combination. Here's the linear combination with the Lagrange multipliers and each of the constraint functions from this constraint. And then we have the next set of linear combinations between the lambda i's and this constraint function. Right? So they have two different sets of these linear combinations of constraint functions because we have these two different sets of constraints. So that's the Lagrangian. So the primal problem is the inf of the soup of the Lagrangian. What variables will we take the soup over to get the dual function from the Lagrangian?
Soup over
Lambda alpha.
Soup over lambda and alpha. To get back the original primal problem, we take the supremum over these new dual variables, these new Lagrange multipliers. So the new ones are lambda and alpha. So we'd have a soup over lambda and alpha. We can just do some algebra on this and clean it up a little bit. Get to this form. So we've collected all that. We've collected things a little bit. And it's the primal formulation, the inf of the soup. And then, of course, the dual is swap the two. Soup of the inf. And I've written the inequality for that weak duality stuff. So one thing we can ask is, do we have strong duality here? Yes, you're so sure already. How do you know this?
It's convex.
Yes, it's a convex optimization problem. We went through that. But most convex optimization problems have strong duality, but not all. There's some technical condition we have to check.
Affine constraints.
OK, so we have affine constraints. We have a convex optimization problem with affine constraints. And there's a particular constraint qualification for affine constraints, which was what?
You need to have you don't need to have strict
feasibility.
Yeah. So as long as we find at least one point which is greater than or less than or which satisfies the constraints with either less than or equal.
OK, so the most general version, which works for any kind of constraints, is that we need to find some strictly feasible point in the domain, which we'll be able to do for here. But as you pointed out, for affine constraints, we don't even need strict feasibility. We need to find any point that's feasible, which is pretty minimal. Both of our constraints are affine. So let's look at it. So this is convex, good. Everything's convex. So we need to find some point that's strictly feasible. What variables are we looking to set? Just to make sure we're following here. Which of these many, many letters are we going to need to set and decide that they are strictly feasible?
W, B, and X.
Yes. So in this context, we're looking at our constraint functions as functions of our optimization variables. Our optimization variables are now W, B, and psi I. Okay? And so we're looking for some setting of W, B, and psi I such that these constraints are satisfied. That'd be a feasible point.
So as long as we have less than, if W, B, and psi I, which is apparently n plus d plus 1 is less than 2n, less than or equal to 2n, we have more equations than unknowns.
Okay. I think you can directly set things, directly set W, B, and psi, and
Just make psi really big.
what's the second?
So set W's and B's to 0.
Okay, so here's an idea. Set W and B both to 0, and so what does that do right away? This sets this to 0, that becomes 1, and psi I to be 1. So if psi I is 1, negative 1 is less than or equal to 0, great. Over here, we've set W and B to 0. That sets this parenthetical expression to be 1, and you set psi I to 1. So 1 minus 1 is less than or equal to 0. Yes, 0 is less than or equal to 0. So it's feasible. That's all you need because this constraint is affine. If this weren't affine, you'd make psi a little bit bigger and you get strict feasibility. But that's it. Okay? So we have found a point that is feasible for our affine constraints. And so we have, that's Slater's condition. So we have strong duality for this optimization problem, which is great. So that means that we can work with the dual optimization problem, and any results we derive from the dual will apply for the primal. Okay, good job. Okay. All right. So let's go back to finding the dual optimization problem. So remember the dual function. So this is the dual optimization problem. Remember the dual objective function is this inner piece, the inf over WB and psi. So that's what we've written here, the dual objective function. We're infimuming over WB and psi, and we're left with this function of alpha and lambda, which are the dual parameters, the dual or the Lagrange multipliers. And so how do we minimize that? So here's our expression. So if you look at this a bit, you'll find, I mean, we've looked at all these pieces before, and every term is either quadratic or linear in WB and psi I. And so we're really, and we're trying to minimize this, we're really in the middle of like a kind of calculus 3 problem, where we need to minimize this fairly straightforward differentiable function. And so is this thing convex or concave? Convex. Yeah, so the leading term is W, basically like W squared, W transpose W. It's kind of a paraboloid facing upwards. This is convex, which is good because we're minimizing it. So the minimum of this, any local minimum will be a global minimum because it's convex. And we can find local minima by differentiation. So we're going to find all the derivatives with respect to WB and psi. Set them to 0. Those will be our critical points, but there will also be, that will also be the global minimum. Okay. All right. So I've worked out this derivative. I mean, it's trivial, really. So we're first differentiating with respect to W, setting that equal to 0, and we get this constraint, and we find an expression for W in terms of some other variables. This is actually very interesting. We're going to come back to it, but for now, I'll just write it down as a relation between W and the other things occurring in our problem. And we take the other two derivatives, and we get more relations. And then the next thing to do would be to take all these relations and substitute them back into this problem and this will give, so when these relations are satisfied, they are satisfied for the infimum. And so we can substitute this back and get an expression for the infimum for g of a lambda. And after some massaging and going through a few steps of equivalent optimization problems, kind of like we've done a few times already, we get the following form for the dual. So it's now a dual optimization problem, so it's a maximum, a supremum. We have this objective function. So what are the optimization variables in this problem? Alphas, right? So this is, at most we have alpha I, alpha j. So this is quadratic again, quadratic. And these terms, so we have some constraint, we have some equality constraint. And this kind of basic range constraint. OK. So now we're going to put, so already things are a little bit interesting. If we combine this thing, so let's focus on that. So this is a relation that needs to be obeyed for us to have an optimum of this in this dual, in finding the dual objective function. W is this linear combination alpha I, yi, xi. Xi is the vector, input vector. Yi is the label, 1 or -1. Alpha I is Lagrange multiplier, also a number. So this is saying W is a linear combination of the xi's. W is our solution vector, right? So our prediction function is W transpose x plus b. So this tells us that at optimality, for W star, we're going to have W be this particular linear combination of the input vectors xi that were found in training, so the n training vectors. So for any, if someone gave us the dual solution, alpha star, we could write down the primal solution, W star, which is what we want to do our predictions, as this linear combination of xi's. That's interesting. This has a name. This is often called W star. We say W star is in the span of the data. That's a term you'll come across a lot. So it means that they're saying it's a linear combination, or a linear combination of the training data points, training input vectors. So that's interesting. Let's combine this with this other part of the dual optimization problem, which is that alpha i's are bounded between 0 and c over n. So I wrote down the SVM optimization problem this way. And I parameterized it a little bit differently than we usually parameterize penalty problems. Do you see what I've done a little differently here? What's our regularization parameter here? What parameter, when tuned? C. Yeah. Right. Well, so half is in the place of the regularization parameter, but there's one free parameter in here, which is C. So usually, we have a lambda multiplying the regular. This is the regularization term for sure. So usually we have a lambda multiplying the regularization term and then just the average loss. But here we have this free parameter c multiplying the loss and nothing but a half in front of the regularization term. So this doesn't matter, right? This is the equivalent. As you sweep over all possible values of c, we'll get all the same solutions as if we had put a lambda over here. Just this is the more, for whatever reason, the more conventional way to write the SVM objective problem, objective function. But it would be kind of exactly equivalent to put the set of solutions you'd get as you varied c are the same as if you put lambda over here and varied lambda. If you have a very large c, what would you expect a very large or very small lambda to be equivalent? Yeah, right. So if you weigh this very heavily, that's equivalent to weighing the regularization very little, right? So it's a simple reformulation. OK, sorry I didn't mention that earlier. So c is like a regularization parameter. And just to be clear, would c heavy regularization corresponds to c large or c small? C small, yeah. Good, OK. So heavy regularization. C is small. That keeps alpha I small, close to 0. Now W is this linear combination with parameters alpha I. So for regularizing very heavily, our alpha i's are close to 0. What does this say for robustness to outliers in our training set?
More robust. If we have a small c, then we'll be weighing each input smaller. We'll take.
Right. So the impact of any single training example, the ith example, is somehow bounded in its effect on W star by the fact that alpha I is constrained to be close to 0. So the smaller c is, which is to say the more we're regularizing, the more, yes, robust we're going to be in the sense that the less effect any single example can have on W, our optimal solution. So I think that's the first interesting insight we can get from the duality study. All right, so the second to last thing we're going to look at is insights we can get from the complementary slackness conditions. And this will be fun. You can just read them out from the complementary slackness conditions if we set things up right. So let's introduce f star of x as this affine function that gives our prediction corresponding to the optimal W star and B star. Remember, this is our margin picture. Incorrect is anything to the left of 0, right? To the right of 0 is correct, but there's this thing between 0 and 1 where we have some margin loss. We have some loss, but we're getting it correct. OK. So we'll call it a margin error for less than 1. Anything less than 1 is a margin error. On the margin will be exactly 1. And this is not standard terminology, but we'll say the good side of the margin is whenever strictly greater than 1. Okay. So psi I star, we don't know why yet, but sometimes these are called slack variables. And so remember, psi star is that maximum, right? The loss, the hinge loss on the particular example, xi, yi. And let's just work through some examples. Suppose psi I star is 0, so the slack variable is 0. Then what does that tell us about yi f star xi? Yi f star xi is what? That has a name we've already defined.
It's margin.
Margin. Yes, it's margin on the ith example for the optimal prediction function f star. Great. This is margin. So claim here is if the slack is 0 for the ith example, then the margin is greater than or equal to 1. Do we see why that's the case?
Yeah, because if it is, otherwise the maximum will be will be the second term. So therefore, psi is not equal to 0.
Great. So if this were not true, you're basically saying if this thing is less than or equal to 1, then 1 minus yi f star xi will be greater than 0, and so the maximum will be greater than 0, which it cannot be because psi star is 0. All right. So we're kind of reading off that of course, if the slack is 0, then the margin is greater than or equal to 1. That makes sense. It's completely obvious from this picture also. If psi star is, so if the loss is 0, then we need to be at 1 or greater. That's what we're saying here. Okay. All right. So we're either on the margin, so exactly to 1, or on the good side of the margin. Great. All right, now let's go towards complementary slackness, which means we need to remind ourselves what our Lagrange multipliers were and the constraint functions. And remember what complementary slackness was?
Lambda I, so the Lagrange multiplier, optimal Lagrange multiplier multiplied by the
constraint function
is 0 for all.
Right. The product of the Lagrange multiplier and the constraint function is 0 for the optimal. Good. So here I'm recalling another one of those first order conditions. If I went back 7 slides or something, we'd find that for optimality, when we computed the gradients to get the dual objective function, we found this relationship between the slack variable and C over n and alpha I star. Fine. And then this will be useful. And then the complementary slackness conditions are these. So the optimal Lagrange multiplier, and then this constraint function, and lambda. So lambda I star, because it needs to be the optimal, times negative psi I is 0. And then I've plugged in this for lambda I here. All right. So these are our complementary slackness conditions, which turns out we can read a lot of interesting things off of. OK. So for example, so these are the slackness conditions again. So if yf star xi is greater than 1, so if the margin is greater than 1, so strictly on the good side of the margin, then the margin loss is 0. Yeah, because the loss function is 0. And we get alpha I star equal to 0. Well, that's interesting, this last part. Do we see why this alpha I star is the coefficient of the ith? Remember, w star is this linear combination of the xi's. Alpha I star is the coefficient in that linear combination. So that would be interesting if this were true. So can we derive that from these equations? Say again? We're trying to show that alpha I star is 0 if the margin on I is greater than 1.
Alpha I can't be negative, and then in the first equation, if yf star xi is greater than 1, and at the same time xi star is equal to 0, then we will have some alpha I star times some constant equals 0. So alpha I star is 0.
So if you can show that this thing is non-zero, then we'll be done. OK. So psi I star is 0 because we're strictly greater than 1. So psi I star is the loss on the example. So if this is greater than 1, then the loss is 0. So that's psi I star is 0. Yif star is greater than 1. This is 0. 1 minus something greater than 1 is negative, strictly. Negative times something has to be equal to 0. Alpha I star has to be equal to 0. That's how we work it out. OK. Let's go and do another one. So margin is less than 1. So we have some loss. We have some margin loss. So margin loss is, yes, greater than 0. And so alpha I star is C over n. Remember what C over n was? It's the upper limit of alpha. It's the highest value we can possibly assign to an alpha. So do we see why this is the case? That's simple. So psi I star is greater than 0. The whole thing has to be equal to 0. So this must be equal to 0. So alpha I is C over n. Interesting. So far we found if we're on the good side of the margin, the coefficient is 0. We don't even need to look at the input data point at the solution. If we're on the bad side of the margin, we're getting any kind of margin loss, then we're maxing out the coefficient on that input vector. All right. Alpha I star is 0. Now we're kind of going the other direction. Alpha I star is 0. So the solution has 0 on a particular input. And then we know that means that we must have no loss. Psi star has to be 0 because why? Great. So if alpha star is 0, this times something has to be to 0. So this is non-zero, so this must be 0. OK, which implies no loss. Great. And so how do we read this? This should have a, yeah. The margin is strictly greater than or equal to 1. No, the margin is greater than or equal to 1. So no margin loss. So do we see why this is the case?
It goes back to the definition of psi I star. So not through these equations, but from the definition of psi I star.
Great. So psi I star is 0 implies, so that's the loss. And so it's only 0 when we're greater than or equal to 1 at margin. OK. All right, I think you guys get the idea. of how you can read these things off. So I've collected the results you can get like this. So it goes in two directions. First, we go from the coefficients. Remember, let me just write this down so you guys remember. W star is this sum alpha I star yi xi. Xi are the input vectors, y is the label, plus or minus 1. So if we look at the coefficients of the ith example, if a particular example has coefficient 0, we know that example has margin 1 or larger. So there's no margin loss. All right, so if the thing is left out of if the example is left out of the linear combination, it must not be getting any loss. If it's between 0 and c over n strictly, means we're exactly on the margin. That's interesting. I find it interesting. So that means the loss is 0, but if it were any less confident, we'd have a loss. And so if we're at the extreme, we know that we're on the wrong side of the margin or exactly on the margin. All right. In the other direction, this is if we're on the good side of the margin, we know that the coefficient for the example is c over n. If we're exactly on the margin, we don't know anything. And if we're on the good side of the margin, we know the coefficient of that example is 0. All right. So it seems like we get these 0 coefficients coming up as a possibility. And that is what leads to the term support vector machine, actually. So if our solution W star has this form, some of these alpha i's can be 0. And the ones that aren't 0, those are the ones that are like left standing. Those are called support vectors. So one interesting property of support vector machines is that we can often get solutions that are very sparse in the alpha sense. So like a lot of the alphas can be 0, which won't make W sparse, but it'll be in a certain representation as a linear combination of the inputs. It'll be sparse in the linear combinations of the inputs. So whereas like L1 regularization gave us solutions for which W was sparse, using the hinge loss gives us solutions that are sparse in the data. So that when we write W as this linear combination of the input data points, which we can do, it's sparse in that linear combination. This might be good. Yeah, go ahead.
So for finding the optimal solution, is the dual always easier for SVM? Or?
So for finding the optimal solution, is the dual always easier? I mean, actually, for us, we'll find that the primal is easier computationally. Traditionally, so one of the original best algorithms was this thing called SMO, sequential minimum optimization, and that works in the dual, and it was and it worked for the case of a kernelized SVM, which we'll talk about next week, which is, I don't know if I'd call it a generalization, but I think most solvers these days work in the primal.
So I'm trying to interpret this, which seems very interesting to me. In the previous slide, for example, so basically, if our classifier is extremely confident in classifying an input, you don't have to look at that input because the alpha I star is 0? Yes.
So the comment is, you don't have to, if you're very confident, you don't have to look at the input. In a certain sense, yes. The sense being that if you took your training data, your original training data, and you throw out all the points that are, you take your original training data, you fit your SVM to it. Then you throw out all points that are labeled with high confidence, so margin strictly greater than 1. Then you'll get the same fit with the remaining training data points. It's an interesting consequence.
So in a sense, the ones which we are extremely confident about are very obvious and so don't provide us any meaningful, meaningful predictive value?
I think that might be a way to look at it. I mean, there's some other points that capture all you need to know. might be another way to say it.
I mean, it's because our loss function is flat there, right? So there is no.
The loss function is flat, so any little perturbations of your prediction function have no effect on the objective when you're strictly bigger than 0 for that data point. So the xi examples that correspond to the alpha I star is greater than 0, so where they still are included, those are called the support vectors. OK. So there's one last piece, which is the B star. So from all of our derivatives and such, we know how to go from the dual alpha I star solution to get W star, but we don't actually have an expression for a B star. So if we want to have a B star, we have not quite finished the job, unfortunately. But it turns out that complementary slackness can show us the way. So here again are our complementary slackness conditions. And then let's suppose, for starters, that there's some example I that has a coefficient strictly between 0 and C over n. All right. So the second, let's see. So this should imply that psi I star is equal to 0. Do we see why that's the case? Sure. If alpha I is strictly between 0 and C over n, this is non-zero, so psi I star needs to be 0. With psi I star equal to 0, alpha I star strictly between 0 and C over n means this 1 minus the parenthetical expression needs to be 0. Psi I star is 0. 1 minus this thing must be 0, which means the yi piece, that's the margin piece, has to be exactly 1. All right. So for alpha I strictly between 0 and C over n, this margin has to be exactly 1. And it turns out we can rearrange this a little bit. If you note that yi is always plus 1 or minus 1, if you multiply both sides of this by yi times itself is always 1, because y is either positive or negative 1. So we get this expression. And that gives us an answer. So B star is yi minus xi transpose W star. All right, so there's an expression for B star. Does this look strange to anybody?
Depends on what.
It depends on a particular I, which is odd. It's like take any I for which the example's coefficient is between 0 and C over n, and that gives you an answer. So does this, yeah?
But I guess would that be because that would be the same for all I?
Yes, so if we trust the math, which one should,
Support vectors, right?
yi minus xi transpose W star will be the same no matter what I you choose. Seems kind of funny. Well, certainly, this only includes support vectors, that's right. And not even all support vectors. There's some support vectors that'll have coefficients C over n, and we leave those out.
I don't think it's that strange because, well, yi and xi are all training data and we all know them. We know them all. And w star is defined in a way that's dependent on i's as well. So it might.
Yeah, I mean, it has to work. Yeah, so it's good. So sometimes people take all the i's and average because they think it'll be more numerically stable. That's this. And then the only question is, what if there's no alpha I star in this range, 0 to C over n? And this is a bit of there's like a research paper on this stuff. And it turns out that these are rare degenerate training problems. And if it's the case that you cannot find an alpha I in that range, then the solution anyway is W star equals 0 is the SVM solution. And there's a reference here at the bottom if you want to follow up on that. All right. So that's all about SVMs except for this one last slide, which is a bit of a teaser for our next lecture. And let's go back to this SVM dual formulation, which because of strong duality, this is actually equivalent, right? And what I want to draw your attention to, that in this objective function, the input vectors x only show up here. And this xj transpose xi, that's an inner product between two input vectors. And because the x's only show up as inside of this kind of inner product with some other input vector, what one can do is imagine, what if we replace this inner product with some new inner product? This is the standard dot product, right? But there's lots of inner products one can define. You can weigh each coordinate of x differently, for example. And kernelization is kind of the study of what you can do if you have an objective function that only depends on x's through inner products. And if you formulate your entire machine learning problem just in terms of these inner products between x's, then you're free to swap out and try different inner products. And that becomes kind of part of your model search. And this will be our first kind of somewhat nonlinear model that we're going to talk about. And it's kind of, I kind of call it pseudo-nonlinear because all the methods are linear. But in the same sense as when you make nonlinear basis functions, you get nonlinear prediction functions. In kind of a similar way, you get nonlinear prediction functions by swapping out different kernels for this basic Euclidean kernel.